Alright, so I keep bringing up constant and non-constant accelerations, and when we have a constant acceleration, that means we can use our constant kinematic equations. I wanted to do an example that gives us a function back of something. So, like, the goal of all of this is you have forces, right? Free body diagram, Newton's second law, on all the bodies in all directions of interest, and that gives us the acceleration. From the acceleration, we can find much more information, right? The acceleration has been constant every problem we've done so far, and that's not always going to be the case. In this class, I think it will be, but I want to introduce you to the fact that it does get harder. And even things like spring forces, we can find instantaneous accelerations, but since the force on a spring is actually a function of the displacement, then that means the force is changing. So we can't get a constant acceleration for the whole distance of travel of the spring system. We can only get an instantaneous acceleration. So I want to show you what you can do if you do get a function. It is still solvable. So we're going to take a cannonball. You're going to shoot it out of a cannon straight up. Alright. Want to know how far it goes, how high it goes. What is its maximum height, delta y? The first case is with no drag. In that case, if we did a free body diagram on this mass, or this ball right here, we just have mg pointing downwards. That means we have a minus mg is equal to, this is Newton's second law, is equal to the mass times the acceleration, and that shows us that the acceleration is equal to g. Well, since that is a constant value, we can jump straight to kinematic equations. Let's say v final squared is equal to v naught squared plus 2a delta y, and solve it for delta y. In this case, we had an initial velocity of 50 meters per second. The maximum height would occur when this final velocity went to 0, and we get a maximum height of 127 meters. Okay, now let's say we have another force. We have a force of drag, and what we see here is it's a function of its velocity squared, and I mentioned that before, and it's a coefficient out front. The coefficient has to do with the shape. You can get that coefficient from a table. I want to say a cone is one of the most aerodynamic shapes, and then it has to do with the radius of the cone, but you can find that value for just about anything. And I think there's other ways to calculate it. They're telling us, well, you got this value, there's 0.01, and that is the force that's applied is going to be that times the velocity squared. So let's do a free body diagram. We have mg going down, and if we shot this thing in that direction, drag and friction work the same way. They always oppose motion, so you might want to draw drag going the opposite way, but they're actually going to be going the same direction. Alright, let's Newton's second law it. Newton's second law. I have minus mg minus the force of drag is equal to mass times the acceleration. We had the force of drag given to us as 0.01 b squared newtons, and we can substitute that in here. We get minus mg minus 0.01 v squared is equal to the mass times the acceleration. So this poses a problem right now. We don't know what the velocity is right there. We haven't even found the acceleration yet. And let's examine this a little closer. Velocity is, by definition, the first derivative of position with respect to time. Acceleration, the thing that we're typically interested in, is equal to that second derivative with respect to time. So if I substitute those in here, I get a dy dt right here, don't forget to square, and then I get a second derivative right there. This is a differential equation. It's relating something's first derivative to its second derivative. You'll take a class on how to solve those. But in this case, actually, if we leave it as minus mg minus 0.01 v squared is equal to mass times acceleration, and then solve for acceleration, we can actually work with it by using some of our very first definitions that we ever introduced. So I get an acceleration equal to a negative 0.001 v squared plus 9.81 when we stick in the numbers. This is not constant. This is what I'm trying to show you. We can't just magically find the speed either. We can using energy methods actually, but not with the force of drag acting on it. Not in this particular problem. We couldn't just find this and stick it in. And if you thought you could, that you're probably not finding the velocity at that instant. So this, what this is saying is that the acceleration is changing every instant, or in this case, every incremental velocity. So as the velocity goes up, the acceleration changes, and it changes as a function of v squared. So it's pretty drastic. You're going to get if it's going really fast, long v squared, you're going to get a big acceleration back in the opposite direction. If it's not going very fast, you'll get a much smaller acceleration in the opposite direction. Okay, but what can we do with it? That's the whole point. It's really not too tough. It's not out of what you guys know how to do this. I'm surprised it's not in the book. I really just wanted to show you all this because it's not really ME242 material, although this is coming out of my ME242 book. We can say, hey, remember, velocity by definition is equal to what, ds dt, change of position with respect to time. Acceleration by definition is equal to dv dt. I did this for y'all too. We can set each of those equal to dt and set them equal to each other, and we get v dv is equal to a ds. We have the acceleration as a function of velocity right now. So what we're going to want to do is get the acceleration and dv together. So I'm going to move ds on the other side. V over ds is equal to the acceleration over dv. Okay, we're looking for the maximum height. I'm going to flip this. ds over v is equal to the acceleration to dv over the acceleration. And let's go ahead and move v back over here. Yeah, this will give us maximum height. Sorry, doing this one on the top of my head. We'll get ds is equal to dv times the velocity all over the acceleration. And we have a function for this acceleration. I'll copy it back down. Alright. Plugging in, I get ds is equal to v dv all over, this is a function of velocity, so now we have all the velocity terms on one side, all over negative 0.001 v squared plus 9.81. Now we can just integrate both sides. We want to know what happens when something reaches its maximum height. The velocity goes to 0, and we can call that y max, right? It's maximum height. If it started at 0, we want to know when it goes to y max, so we'd integrate from 0 to y max. And then this, we'd integrate the velocity from its initial velocity, which they told us was 50 meters per second, to its final velocity of 0, which would be where it turns around and starts coming back down. Now, this is not a solution that you'd be able to get right off the top of your head, but we would, on the left side, we get y max minus 0, or the displacement, is equal to the integral of all this stuff. It ends up being 500 times the natural log of v squared plus 9810. And this is a function of v. Now we need to evaluate it from that 50 meters per second to 0. And after doing so, right, that would be just a refresher in case y'all don't remember what evaluating means. That would be taking the upper limit and subtracting the lower limit. So 500 times the natural log, and we put 50 squared plus 9810. And if you do that, you will get the maximum height of 114 meters. So initially we got, where'd it go? 127 meters. That was with no drag. That's how far it went. That's how high it went. With drag pushing back down on the cannonball, and the acceleration due to gravity pushing down on the cannonball, it didn't go as high. It went 114 meters. Now this is not going to be on your test. I just want to show you that we don't have to have constant accelerations, but if we don't, we actually have to put them back into our original definitions and create new equations. I derived the constant kinematic equations using this equation and this equation, if you remember. We can get one of them, v is equal to ds dt. Well, we can say ds is equal to v dt. And then I need the other one right here. Acceleration is equal to dv dt, or dv is equal to the acceleration times dt. If I integrate both sides, I get v final minus v initial is equal to the acceleration times delta t. And that's one of our equations right there. V final is equal to v naught plus the acceleration times time. If I take that and plug it in here for v naught plus acceleration times time, all times dt, and integrated this, that's when we got s final minus s initial is equal to the initial velocity times time plus 1/2 acceleration times time squared. But this was for constant accelerations. So what I just had to do for this one is come up with our own equation using a definition. So you can always go back to acceleration is equal to dv dt. You can always go back to velocity is equal to ds dt. And put like variables on each side. In this case, we put all the v's on one side and we put the s on the other side. We got two different integration variables, one on each side, and we were able to integrate it to get a solution. And I could have put in any velocity that we wanted to know the distance. So if it was launched at 50 meters per second, and we wanted to know how high was it when it was going 10 meters per second, we just put a 10 here. We could have integrated knowing y max and knowing where it started from and gotten the velocity. So acceleration is not always constant, is the message I'm trying to say. It typically isn't. So just know when to be on the lookout for it. We just solved this expression for the acceleration, or this problem for the acceleration, and when we did it, we got this right here. We got a function of v with no v to just plug in, right? It could be, the acceleration could be a function of position too. In this case, it was a function of velocity. It can be definitely a function of time. All of these things, it can be, the acceleration can look like any kind of thing you can possibly plot on a graph. How about that? Not just a parabola like we've been looking at. It can be anything. And that's because forces can be anything, right? I can apply a force on a book in any kind of pattern I want. I can push on it and let go. I can push and pull on it like this. I can just apply a force. I don't know, it's endless, right? I can slowly push harder and harder and harder up to infinity. There's so many things I can do. And that corresponds directly to our acceleration, right? They're directly proportional.